And I know that you guys all came to see a panel discussion on human capabilities in space. Unfortunately, none of the panel was able to travel, so I got to take over the panel. So what we're going to do is I'm going to talk about the Mars Campaign Office. We are the technology development program for the Exploration Systems Mission Directorate at NASA, which means that we're doing all the technology development needed for human exploration of deep space. So I'm going to talk about what we're doing. I'll spend about 20 minutes doing that, and then I will take questions from the audience or from online or whoever about what we see as the future for human exploration for Mars and what needs to happen. So hopefully everyone's okay with that. If not, now's your time to get up and leave. Okay. Let's see, I have control of the charts. Okay. All right, so the Mars Campaign Office consists of 5 different domains where we are developing those human exploration technologies. We are executing this tech development on analogs and on areas where we can get the most correlatable environment. So that includes the ISS, that includes ground analogs, and that includes ground tests wherever possible. We integrate these technologies across the plans across the agencies. I think that, that our Space Technology Mission Directorate has been road mapping technology development for missions to Mars for many years. So we utilize that as well as the technology gaps as defined by the architecture description document that our Strategy and Architecture Office puts out in ESDMD. So we identify those technologies, we use those documents, and I track the touch points between what is happening in the Artemis campaign and what needs to be completed before we do a human mission to Mars, and make sure that those things correlate together and we're ready to go when we're ready to go. So the 5 domains within the Mars Campaign Office are environmental control and life support systems, crew health and performance, Earth-independent operations, surface systems and environments, and vehicle transportation systems. And I will go and talk about each one of those independently. Okay, first area, which is the one that you guys all came to listen and hear about, is the crew health and performance area. So that is subdivided into several portfolios, the first being food systems. Obviously, food is one of our highest risk items for extended missions to Mars, for crewed missions to Mars. There are a lot of open questions about how we will store food, how we will pack food, how the food will be dehydrated and rehydrated. Right now on ISS, we do a lot of thermally stabilized food. Thermally stabilized food has a lot of water content in it, so one of our areas is trying to reduce water reduction, reduce the amount of water within the food, so you don't take heavier food, and then you can also utilize the water that is within your closed loop water system. So you want to make sure that you're not bringing extra water, you're taking all the water you need. It's one of your heaviest things. Crew health countermeasures. So this is the area of exercise, sensory motor. We're doing a lot of work on balance training. So when crew does return to partial gravity or full gravity, that not only will they be fully conditioned to be able to execute the mission, but they will also have practiced or at least understand the difference between, the microgravity and the gravity environment to be able to maintain their balance, maintain the ability to drive, steer vehicles on the surface, items like that. So we are testing on ISS, we will be testing on ISS, the E4D, which is a multimodal exercise device. We tend to think that for a Mars transit vehicle, we will not have room for a large treadmill, which is what they use on ISS now. So we're trying to do a multimodal device that will allow for rowing and other activities for exercise to maintain conditioning. And we're also doing a balance trainer and some other areas to get the crew prepared for their missions. Exploration medical. So this is really where we are providing medical support to the crew in a large time delay environment. So crew right now, if they have issues, medical issues, need to talk to a flight surgeon. It's as simple as calling down to Earth. It's a real-time conversation that will not be possible on a long mission to Mars. You will be, up to a 20 to 40-minute gap between a conversation. So we need to provide not only medical decision support, we also need to provide all the medical equipment, including pharmaceuticals, including IV fluids, including all sorts of diagnostic tools, so the crew will be able to self-diagnose, or at least self-diagnose to a point where they can then have a asynchronous conversation back with the ground about how to treat themselves. So right now we are getting ready to fly a mini IV generation device. We also have software development for the crew decision support for health and medical. We are currently doing some work on spacesuits, and this is specifically for Mars spacesuits. So this is a slightly different environment. I'm sorry, it is a hugely different environment and a slightly different suit than you would use for lunar. So there is a dust problem, and I will discuss that more, but it's different, right? The lunar dust is very abrasive, there's different issues, it kind of gets everywhere. The Martian dust, the Martian regolith, has different chemical composition that is actually that we have to protect for on the crew. Fire safety. So the areas we're doing in fire safety, we have a full suite of fire safety items. We want to concentrate on fire prevention, monitoring detection, suppression, and cleanup. Cleanup being the very important part of it as well. So we have testing going on. We have done partial G testing. We've had partnerships with our biological and physical sciences folks to make sure that we understand how fire propagates, how to detect it in a partial G environment, and especially within the exploration atmosphere, increased oxygen environment. And then finally, we do quite a bit of work on our radiation protection. So we have a three-pronged approach with radiation. We do space weather analysis. We have partnerships with the Goddard Space Flight Center and work on and help and fund some of their modeling efforts. So we get prediction and time to effect for solar particle events, anything that might affect the crew that would require them to take cover within a shielded area. So we do also transport models to help design those shielding systems. And then we also have detection, proton and neutron monitoring systems that will allow for earlier detection of events, especially when they occur on the opposite side of us when we're in opposition. We will not be able to predict, we will not be able to use our space weather prediction capabilities because we will not have visibility of that side of the sun. So they will need some early detection devices that will allow them a couple of minutes to get into a shielded environment. Okay, Earth-independent operations, and this is a software development area, and then two areas of hardware development. So overall, this is a software suite that will allow for fault detection, isolation, and resolution with crew involvement. Again, back to our ISS example, the crew, when they have problems with hardware, especially life support systems, electrical systems, on orbit, on ISS, are able to call down to the ground, and the flight controllers are able to help them identify the problem, troubleshoot, and come up with resolution. And then also, if stuff needs to be taken offline, you also have a replacement options, right? You can get stuff back up to ISS in a fairly expeditious manner, considering. So what this Earth-independent operations area is going to do, and is working on doing, is first building not only digital twins of, right now, electrical systems and life support systems, but also utilizing current knowledge of those systems, using hazard reports and expertise and expert inputs to be able to develop using large language models and AI to determine what those anomalies may be and give suggestions to the crew. Then what they will also be able to do is use a generated suite of procedures to generate a path that the crew can follow and isolate and resolve the problem. They are working with the flight directors, with Mission Control Center, to work that crew interaction part of it and how that would look. They are also going to, in the data integration area, they are taking the large suite of data that exists right now, all the ground test data, all the flight data we have for our systems, life support systems, electrical systems, and pulling that in and building that large language model and AI based on that, and allowing that to be able to go with the crew, because that is another thing that right now most of your AI large language model work can be done on ground because there's access to all the databases and all the computers you need. You won't have that. You'll still be on your 20-minute to 40-minute lag. So being able to take all that information along with you is going to be important. We are also working in the vehicle systems area to improve our instrumentation. So adding additional instrumentation onto life support systems will help with that fault detection. So we're developing new instruments and installing those instruments on ground test systems and other areas to make sure that we are able to provide accurate information to the crew. And then finally, we are moving into developing some new areas in comm and nav. This sort of is a natural outcropping from the Earth independent operations because there does need to be large bandwidth data streamed between the crew vehicle and the Earth. So comm becomes one of our forcing factors for that. And then also providing navigation aids. One of the areas we're moving into is is providing a clock, an atomic clock for nav purposes that will be able to be used both in lunar and for Mars operations. Okay, our biggest portfolio area is environmental control and life support systems. So 3 areas, but all very interrelated. Life support systems is developing mid-technology, mid-TRL items to get ready for testing and on the ISS or in relevant ground environments. Eclipse Evolution is our partnership with the International Space Station where we have been upgrading and items, life support systems items on the ISS components with the goal of reducing maintenance, with reducing need for crew interaction and reducing the need for replacement of parts. So really increasing maintainability, decreasing part count, and making those items prepared to go for a mission to Mars where your logistics situation is much more difficult. And then finally, logistics reduction. And that is where we are trying to provide the nuts and bolts of how you would really live and work on for a 2 to 3 year mission. That includes how you will deal with garbage, how you will deal with your inventory, how you will track your food, things like that. And so we do a lot of work in that area to make sure that folks know where items are, and we test. We currently have an experiment, not really even an experiment this anymore because it's actually being used, of tracking with RFID tags all of the consumables on the space station. And so we anticipate continuing doing stuff like that and making sure we're tracking everything, what everyone's eating and using on a Mars transit mission. Okay, one of our new areas that we're moving into in this next fiscal year is surface systems and environments. And this is really where we consider the moon to be a test bed for future Mars surface missions. So where we are doing current technology development on that is in power management and distribution. One of the things that worries me the most about Mars missions is that logistics piece of it, is that you have no resupply capability whatsoever. So everything you take is what you have. So one of the areas that we think that is going to be extremely helpful for that is the advanced modular power system, which provides a single box, electric box, that can be adapted and changed given the number of cards and types of cards in it to all different types of electrical boxes. This will reduce the amount of actual unique electrical boxes you would need for replacement or to fix them. You will be able to use the same kind of box, change out your cards, possibly even print out items as you need, because with a additive manufacturing capability, and not have to worry about an electrical problem or anything like that interrupting the mission. We're working on surface water systems. This is an area that we actually have a partnership with DARPA. This is a bioregenerative life support system, so this is using algae to clean your water and to close your water loop. And then also will provide fertilizer so you can do crop growth as well. I mentioned dust, so we are right now working on lunar dust systems. We are partnering with our other exploration programs to help solve some of the dust problems, including dust in connectors, electrical connectors, dust in seals, liquid seals, and also dust as far as the infrastructure is concerned. So the electroresin spray system is a system that you would spray on the ground, and it would sort of create a resin on top so you get a non-dusty road for your rovers to drive over. We're also working on metallic glass bearings, which are dust-resistant bearings that can also survive the lunar night. We have areas of, we're moving into areas for structures, including robotically aggregated structures for infrastructure development on the surface of the moon, which will be useful not only for aggregation as it's needed on the surface of Mars, but aggregation of a Mars transit vehicle in space. And our last area is the one that we have not fully matured yet. As we're sort of building up, we're sort of adding these domains one at a time, but we've started some initial planning work in the transportation and vehicle systems for Mars transit, propulsion, and cryogenic fluid management. So the in-space propulsion system has not been decided yet, so we are trying to keep all options open to make sure that we are ready when we get a reference mission to design for, that we have the idea or the planning for that propulsion system ready to go. It also includes some EDL propulsion system work within that portfolio, and then cryogenic fluid management. And cryogenic fluid management is a huge area, and we definitely see that as a big growth area for the Mars Campaign Office. Every Mars mission, every design reference mission is going to require some sort of propellant storage and propellant transfer. And everybody is working on it. Everybody is working on the long-term storage. I think we can help out with that, and we do see a growth path with that forward. In situ manufacturing, so I mentioned before, if you have all the electronics boxes are the same and you're also able to print electronics, that is going to be very helpful. So in situ, additive manufacturing, and then in situ recycling. So being able to use old trash and old parts to be able to, as feedstock for your new stuff, is going to be very important, as well as being able to do in situ resource utilization and manufacturing with regolith. That's an area we're looking at, or Mars regolith as well. And then finally, that transit enabling. So that's that in-space aggregation of vehicles. That's going to be a big area of growth. Right now, if you can imagine, a Mars transit vehicle is going to be a construction project about on the scale of an ISS without the aid of a space shuttle to help put the big pieces together, and without the aid of crew to be able to build those pieces. So we're going to have to really make some advances in that in-space robotic aggregation so we can build that transit vehicle. And I think that is my last chart. So I will take questions. I think we are going to bring Keoki Jackson on stage, and we're going to sit here and we will answer questions for you guys or questions online. If you have anything you want to discuss, we're kind of wide open. Like I said, this was a panel, so it's now a panel of one. So please welcome Keoki, and we'll sit down and answer your questions.
Okay, Dayna, great to be here, and thank you very much for those remarks. Just remind everybody, we've got up on the screen, use the app there to submit the questions, and so please go ahead and get your questions in, and I'll be able to see those pop up, including how those are upvoted here, so everybody knows the drill. Yeah. Well, let me start off, I just wanted to note that this is an immense systems engineering problem.
It is.
Right? And you talked through many of the aspects in your remarks there. But could you articulate maybe what is the demand signal for the systems engineering to the various participants here, whether they're government, industry, new entrants, and so on, to be able to get after the integrated approach to Mars?
Yeah, so I think we're really, for the systems engineering part of it, because it is a huge systems engineering, one of the things that I am concerned about, I mentioned it several times, is this commonality, is how our systems engineering personnel, our systems engineering experts are able to design a system that is not going to be able to be resupplied, that is not going to be able, that is going to, sort of go off into the ether and with, asynchronous communication and no ability to fix things in the way that we've always fixed things in the past. The way that we have done things on ISS is, like I said, we've always been able to call down to Earth. We've always been able to get replacement parts. We've always been able to manage the logistics a certain way. Now, when we go to the moon, it will be more difficult, but there still will be the ability to resupply. There still will be ability to sort of manage those logistics. So what I need from the giant system solution, I think the other stuff is solvable, right? It's propulsion is solvable, right? Life support systems are solvable. These are all technical things we know how to do, but that systems part of it, how do we design a system that is going to have to not only include humans, all the human factors, but also, again, be sort of not maintainable by any means that we have done in the past.
Well, maybe we can pull that thread a little bit more and break that down. So there's clearly the autonomy, automation, likely AI elements to that. There's also, to your point, the human elements. You'll have the people maybe that are traveling in some of these missions, but then there's the mission support back here on Earth. Mm-hmm. One of the questions that has bubbled up is, how would you handle an Apollo 13 situation? Mm-hmm. Can you talk through conceptually how NASA is thinking about that approach?
So the Apollo 13 situation is something we bring up all the time, right? Because everybody knows that scene. It's stuck out in everyone where there's a filter and there's another filter and they do not work together, then another interface and they do not work together because it was two separate contractors. And for all the engineers in the room, it makes total sense why they were different, right? I understand why they were different, and nobody thought that you would ever use it that way. So it's that one of those things is we need that imagination of say okay, there may be some duct tape solutions that we need to do. We would like to avoid that. How, as systems engineers, as designers, how do we avoid that? If we are truly going to build a Mars transit vehicle with an advanced propulsion system, it is going to be an all hands on deck situation. We are going to not just have to rely on all of our current, American companies to help us, but the international partnerships. It's going to be a huge effort. It will be, in fact, one of the largest efforts that humankind has ever undertaken. So how do you wrap your arms around something that is so huge with so many different players in it and avoid an Apollo 13 situation? And so that it really is one of our biggest challenges. Like I said, the technical challenges, they exist and they're hard, but this one is a really difficult challenge.
Well, I think that's a good segue. There's a lot of questions about technology and particularly technology gaps. And I like this one because it suggests an answer, and I want to get your perspective. It says, what is our biggest gap and why is it ECLSS, so environmental control and life support?
Why is it environmental? Okay.
So is it really ECLSS or not? And what are your perspectives on it?
Okay, so I will tell you, I was a propulsion engineer in a previous life, and when I first started working ECLS, my boss sat me down. I didn't know anything about it. And he said, all right, I'm going to tell you something. He's like, here's the thing with Eclipse. There's not a lot more to go get performance-wise with Eclipse. Same with propulsion, right? A liquid propulsion system, we've pretty much topped out how much performance we can get out of a LOX hydrogen system. It's kind of similar with Eclipse. We've pretty much topped out. We have closed the water loop on ISS. We get 98% recovery. We have a couple more steps to do to close the air loop. So at this point, the biggest worry with Eclipse is that maintenance and reliability. So what we want to avoid is having crew running out of parts to fix things, having to replace consumables, too often running out of consumables. So we really need highly reliable life support system components, which is where we have been developing on ISS those high reliability items. So right now, when we have upgraded or changed the design of items, of life support systems components on ISS, we test it, and then we don't say it's finished until it's run for 3 years on ISS. And then we say, okay, now to the reliability that we think we need. And then we turn it over to ISS for them to use as part of their vehicle system. So that 3 years really gets you to, your kind of outside Mars mission. So I feel pretty comfortable, not that Eclipse is done, but that we can see the path in front of us and it's not unachievable. Where I see other big technology gaps that I'm worried about, one is the in-space aggregation. I think that we really have yet to figure out how we're going to build this giant vehicle in space without much crew involvement and with a lot of international partners, with a lot of pieces having to come together. Propulsion, I think we have plans, but I think there's a lot of development that we need to do on that, especially when we figure out what kind of propulsion system we actually want to use. And then I think really where we have a lot of gaps and really where we're working a lot is in the crew part of it, right? In crew health and performance, in making sure the crew stays safe, the crew stays conditioned. The crew, background, the galactic cosmic radiation is a big worry, right? And the crew is going to be out of the magnetosphere for 3 years. That is a tough time. And then also just behavioral performance, right? This is going to be a crew that's going to spend 3 years together in a tiny, not tin can, maybe inflatable can, but how they're able to, and with very little synchronous communication back to Earth, a lot of asynchronous communication. So how they're going to be able to perform and how they're going to be able to live and work for that long with this tiny group.
Well, I think that sets up, so you've really hit on some of the technology challenges. There's a number of questions that are really around how can we find out more on an ongoing basis, whether it's emerging companies or people who are interested in developing new solutions. Mm-hmm. How do they find out from NASA what are those technology challenges?
Yeah, so I mentioned, and this is my recommendation is if you're, we are always looking for solutions. Technology solutions come from everywhere. The first thing is, like I said, our strategy and architecture office has identified what they think the key technology gaps are for missions to Mars. And those are published, those are public, those are available in the architecture definition document that is on a NASA website. But the other way to get involved, obviously, is if you have good ideas. We do a lot of work with the small business innovative research, so we do SBIRs. We have a couple SBIRs with companies that have come up with great solutions that we want to explore more. We also have current partnerships with traditional space companies. We do encourage, where I encourage people who want to get involved, especially companies or academia, is to really work with the centers. So it's all well and good, and I sort of know what's going on, but the real work is happening at the NASA centers, right? So that's where where the ground test beds are. That's where they're doing robotic manipulation. That's where they're doing the software. So understanding what's going on in the centers, every center has a front door kind of operation, and working with them on areas where you can partner, and ought to be, because I've said so many times, very well versed on what those technology gaps are, and they're working on those.
Fantastic. So there you go. Make sure you're engaging with all of those organizations. All right, we're going to go deep for a moment here because one came in that should take advantage of your expertise in nuclear propulsion.
Okay.
And if I get the acronyms wrong, just roll right past it, so I apologize in advance. So regarding the to-be-determined propulsion method, if you're looking at NTP, NEP, are you considering the cost-benefit, more than cost-benefit analysis between, I believe this is highly enriched uranium, non-proliferation concerns, and high-assay low-enriched uranium? Mm-hmm. Is that HALEU, design complexity and safety?
Yes. That I actually just had a conversation about this yesterday. This is perfect. So right now, SPD 6, Space Policy Document 06, mandates the use of high-assay low-enriched uranium because of nuclear non-proliferation issues. So, it's one of those things. If you actually read the Space Policy Directive, it says you must use HALEU unless you really, really don't want to.
Okay.
However, that being said, using HALEU actually solves a lot of other problems. Performance-wise, I think we can get there either way. You need, for a nuclear, I think we're very much there for like an NEP. I think, fission, they're going to leverage what we're doing on fission surface power. I think we can build an NEP reactor using HALEU easily. I think they've made huge progress in industry on building an NTP reactor that uses HALEU, and it solves a lot of problems. I don't know if you've ever, maybe if you've driven around the South and seen the vehicles that deliver the highly enriched uranium reactors to the Navy. The Navy.
Give us a visual.
So it's an MRAP, I think they call it. That big. It's like basically a tank that drives down the highway with tanks in front and behind them. It is expensive. It is hard to do. You don't want, you really don't want to have to do any of that. And if you do a HALEU reactor, you don't have to do any of that. It really it becomes a much easier problem to solve regulatorily, and then you also don't have sort of that nuclear weapons grade uranium. So if we can do it, we should use the low enriched uranium. If we can't, I think we can have that conversation, and we as sort of a country and as a global entity should have that conversation.
Outstanding. Well, so keeping going on some of these challenges, so moving from propulsion to gravity, okay. What are your thoughts on artificial gravity or partial gravity, and how is that factoring into the mission design? Yeah,
so right now we do not have any technology development in any sort of artificial gravity area. It is the opinion of most of the physicians, the flight doctors, and the people who do the research on it that we can maintain conditioning through exercise. Now it's a lot of exercise. I mean, it's hours a day that they will have to exercise, but we really do think that, especially, like I mentioned that E4D, our multimodal exercise device, we are trying to get the data right now as that gets put on ISS, get that data that will help us understand if we really can get there with just exercise machines and maintain that conditioning. We really don't want to send a crew to Mars and have to be in a vehicle with, their people for a year and then get to Mars and not be able to explore. There's no point in doing that. So right now we're pursuing most of those exercise countermeasures, and we will see where we end up with that.
So no 2001 rotating stations then, huh?
I think that would be very cool, but we're not there yet.
In the second round.
Yes.
Very good. Continuing along, you mentioned a little bit about the psychological effects, and so there's this, just the duration of the mission, 3 folks or more or less in a can or inflatable can. But what about the change between a 24-hour circadian rhythm and then a Martian day? How's the mission team thinking about that?
Yeah, so what we are doing for that is that we actually have analogs. So we are getting ready actually to start another round of our CHAPEA analog, which is a Mars analog. And we have made we do try to maintain as close as possible what it would be like for a crew on the surface of Mars. So the day length, the SOL. We are doing delay of comms. So, and then we're also going to do a delay of medical comms this time as well, which is, this is sort of getting out of our initial comfort area, but we really do need to test and understand when the crew does not have immediate access to flight doctors, how they are able to, work their own medical issues and go through that. So we do try to get as close as possible with these analogs, and the CHAPEA analog is 4 crew members. Get as close as possible, and then monitor their behavioral performance, monitor their mental health, monitor all that. And I mean, it is very real for them. They are away from their families for, over a year for the CHAPEA analog, and they do not get to talk to them, face to face and in a, like FaceTime sort of situation. It is all writing and emails and communication like that. So they are able to learn a lot from those analogs.
Well, maybe as we think about these various challenges and then some of the nearer term missions like Artemis 3, are there opportunities to essentially start doing testing early on some of these things? Yeah,
I think, to pull on the analog, one of the ideas we have out there is to treat the last 2 years of ISS as like a very high fidelity Mars analog. We could really cut back on the, it would take quite a bit of planning and we would really have to commit, but we have been looking at, with reduced a crew that would basically stay up there for 2 years, a reduced resupply option, and really understand better what it's like to get very close analog-wise to a in space 4 years kind of situation for the crew, and how that would, with still the ability to be in low Earth orbit, and if there is a problem, to be able to rescue or talk to folks or bring new supplies aboard. So I think that is really appealing, right? I think that really could help us understand and kind of pull together all these different aspects. An analog, like a ground analog, can test your behavioral performance, it can test your folks, it can even test your food, but then you're not in microgravity, so if you can add microgravity, the closer, the higher fidelity your analog is, the less risk you're taking on for the actual mission.
Okay, well, I want to take so given that opportunity there, I want to go back a little bit to where we started with systems engineering. And this gets to how do you set up the systems and the infrastructure? What goes in sequence, what goes in parallel? How are you thinking about that for the mission?
Yeah, so that's a really good question. And the answer is I'm not. We're not quite there yet, right? Since there are big questions that we need to answer about what a Mars mission will look like before we can decide how we're actually going to do it. So you need to answer, and some of the big questions are, if we're going to go to Mars, when we go to Mars, there's 2 different ways you can go. You can go, it takes a long time either way, but there's a short stay option and there's a long stay option. So are you going to go and just spend a couple of weeks on the surface, or are you going to go and spend like several months on the surface? And those 2, the technology development for those are wildly different, right? How fast do you want to get there? And that drives your propulsion system. How many people are you taking? Are you going to send everyone down to the surface, or are some people going to stay in orbit while others go down to the surface? These are big questions that need to be answered, and when they are, and we answer them the right way with thoughtful determination, then we can start doing the technology development that we need to do those, and then also do that mission planning. Like, how are we going to send a bunch of stuff to Mars to sit first? And then the crew, it'll be ready to go when the crew gets there. Are we going to have a fuel depot at Mars? Are we going to try to, take all the propellant in transit? Things like that. But we have to get those big questions answered first.
So I think all the loggies out there are saying, "Wow, this is great. I got plenty of work to do ahead." I think we're closing in on the last couple of minutes here. So, and we have actually gotten pretty much to all the questions. Okay, so there's one last one that the people are very interested. For you, what is your favorite project or piece of the Mars mission?
Okay, well, I have to go back to what I know. So as we were starting to pull in the vehicle system stuff and the propulsion and cryogenic fluid management, that's where I got my start 26 years ago, so that's like my first love is always propulsion. I actually managed the Space Nuclear Propulsion Project for a while, so I'm very familiar with it. I like it a lot. But I would be remiss if I didn't also add in the life support system area. I had the opportunity to manage the life support system area at Marshall Space Flight Center for a couple of years and to get to know all those folks and get to know how the system works. And I really did have a new appreciation. I don't know, engine people, propulsion people are kind of a little arrogant about them being like have the hardest stuff than they're doing the coolest stuff. But going and working in the life support systems area, I was like, no, this is also very, very cool, and you're doing really interesting and neat work, and the chemical processes are amazing, and how we're keeping the crew alive is so important. So I would say those two areas.
Well, as someone who never did propulsion but did spend a lot of time on human adaptation to the space environment, I'm glad you got that piece in there as well. All right, well, thank you for both a wonderful presentation and then a wonderful conversation. Please, a big round of applause for Dayna.
Thank you so much.